Good morning, my dear all student. Today our topic of discussion in electric drive is induction motors scalar control. This is the case study or this is the procedure which is only applicable for squirrel cage type induction motor. So already I have discussed with you in the last week about the modeling of induction motor. Now I think all of you are familiar what is the basic difference between a squirrel cage type induction motor and phase wound type induction motor. Basically, in case of squirrel cage type induction motor, there is no winding in the rotor, and instead of winding, there are copper bar, and those copper bar are shorted by means of end ring for carrying the current. Now let us start about the scalar control. Now, for studying the scalar control, it is basically based on steady state model. So, steady state model I have discussed in class. Now, steady state model, for studying that, we have to go through the basic equivalent circuit of a induction motor. Now, in case of induction motor, as we are studying it in steady state condition, here Rs is the resistance and L is the inductance. Both are in the stator side, and correspondingly this will be the inductance and this will be the magnetizing current, and correspondingly it will be in the rotor side inductance, and resistance is being shown here as a variable, that means R dash by small s, and this small s is indicating the value of slip. Now here at the input terminal we are giving supply voltage V. Now, scalar control of induction machine. Before studying that, you should know about the torque speed characteristics of three-phase induction motor. So, in this diagram, we will discuss about the torque speed characteristics of induction motor, and from there we will study about the scalar control of induction motor. Here, torque is placed here, and in this axis we have placed the value of slip. Now, as we know that induction motor suffers from a very serious problem of low starting torque. So as a result, here the starting torque value is little bit lower. Now in this region the torque is pulled. This is called pull out torque region, and after that it reaches to the maximum value. It reaches to the maximum value of torque, and after that, instead of withdrawing load, if we increase the load on the motor, in that case the motor is going to shut down. Rather to say, this region is called braking torque region, or withdrawing torque region. And instead of withdrawing load, if we increase the load, after some certain time, what will happen to the motor? In case of induction motor, we know that it never runs at the synchronous speed, because rotor is always try to catch up the same speed of the stator. Now as the stator is running at the synchronous speed, rotor tries to catch up that speed, and it tries to generate much more torque to compensate that amount of load. That rotor will try to rotate much more faster, and when the speed of the rotor and stator will be same, at that condition motor will be shut down. That means at that condition the value of the slip will be 0, and as all we know, when the slip is 0, motor will be shut down. So that is being shown here. Now you can see here, this is a point. This point is known as insertion point. That means at this point TE, or electromechanical torque, that will be equal to the load torque, and it determines the steady state speed. That means up to this point motor is under steady state, but after that if we increase the load, the car pull towards the down and motor will stop suddenly. So let us see. Now, for a given load, T by omega characteristics, rather to say, the torque versus speed characteristics is the steady state speed. That can be changed by alternating the different values. Now, here are the different methods by which we can control the speed of the motor. So, the first method that is known to all, that is pole changing. Pole changing. How the pole changing is related to the induction motor speed? Now pole changing is very much related to the induction motor speed. Why and how? Now as we know, as per the working procedure, induction, in case of induction motor, we just give supply to the stator end, and in the stator end, when we are giving the supply, a rotating magnetic field is produced, and that field is always rotating at synchronous speed. The value of the synchronous speed, or ns, that is equal to 120 f by p, where f is the frequency, p is the number of pole. So rotor is not at all given any supply, and by the virtue of Lenz's law and electromagnetic induction, rotor tries to catch up that synchronous speed and it begin to rotate. So if we able to vary the value of, rather to say the rotating speed value of stator field, the speed of the motor can be controlled. So that value can be varied by varying the number of pole. So the number of pole variation, one of the method by which we can vary the synchronous speed. So as the synchronous speed varies, rotor speed definitely varies. So we can make a discrete step change in speed by varying the number of poles. Second method is variable voltage, variable frequency method. It's a very important method. Specifically, it is known as VVVF control, or variable voltage, variable frequency control. So what is this variable voltage and variable frequency control? Now, as we know that this variable voltage, by varying the input voltage, we can control the speed of the induction motor. Similarly, by varying the frequency, we can also control the speed of induction motor, as this frequency is directly related to the synchronous speed. But there is some problem, that if we able to vary the voltage from 0 to any upper values like 220 volt, in that case, after some steps of increment in supply voltage, the core of the motor becomes saturated. We may increase in the supply voltage, but the speed of the motor will not be increased. So instead of variable voltage, we are going to choose an option which is known as variable voltage, variable frequency control. That is more convenient, and there we get a larger range of variation of speed from 0 to any one value. So this is possible. Why this method is we are choosing, because in this method we are having lots of use of power electronics devices or converter, and those power electronics devices or converter are having very high efficiency. They are very easily available in the market, and due to that the losses of the system will be reduced and efficiency of the system will be higher. That's why we are going to choose for such an option, and this can be operated in low slip frequency region also. That means we can control the speed from very minimum value to the maximum value as per the requirement of the employed or applied field. Now there is another method, that is variable voltage and frequency fixed. This is also very important method. Using transformer or triaxial, slip becomes very high as the voltage is reduced. So in this case it is having lower efficiency. Now variable voltage, fixed frequency. So in this graph here, in this axis we have plotted torque, and in this axis we have plotted watt. Okay, so that means it is we are producing here RAD per second. That means it is omega radian per second. Rather to say, this is the speed per second. So you see here, when the supply voltage is 460, rotor resistance is 0.25. Now for that case we are getting the value 0.5 into 2 pi 50. That means 2 pi 50 means here we are getting the value. This is 2 pi into 50. So correspondingly the frequency is 50 Hz, number of pole is 4. Now for the lower speed, slip will be higher as per the graph. For the lower speed region, speed will be higher, and low efficiency at low speed. So this variable voltage fixed frequency method doesn't yield very good result. Now, variable voltage, variable frequency. It's a very important method. So already I have discussed this diagram in the first slide. Now in this slide, here again we are having the corresponding phasor diagram. Phasor diagram means in this phasor diagram, E or induced EMF is chosen as a reference. V is the supply voltage. This is the Rs plus j omega s into Is. That means this is the complex power, and this is the IR. That means current induced in the rotor circuit. This is the magnetizing current, and this is the stator current. So in between they are having an angle which is represented by delta. Now the torque developed, that is Ki phi Ag sin delta, correspondingly electromechanical torque. So in the very low region, the value of the torque will be KIR phi Ag, sin delta will not be there, and correspondingly torque developed in the very low region, as the value changes or as the value increasing, it will be equal to TE K phi dash phi square Ag into FSH1. Now variable voltage, variable frequency method, again we are getting, if phi Ag is constant, in that case alpha is the slip frequency, T alpha is the slip frequency regardless of the synchronous frequency, because it is not related to the synchronous frequency. Now in this case, if we plot a graph, you will find the torque is in this region and this will be the omega r, that means radian per second, that means this is related to the speed. So if we plot them for the different values of the omega, this is the rated value and this is the corresponding value, slip 1, slip 2, slip 1, slip 2. So corresponding the values, if we draw the line and by joining them, we will be getting the line which is equal to the T load. That means in this position the load torque and developed torque will be counterbalancing each other. Now this is the rated value for the corresponding load, this is the T1 value for the slip 1, and this is again the T1 value for the previous slip 1. Now if we take the ratio, it will be equal to T rated by W slip, T1 by W1 slip, T2 by W1 slip. In this axis, this is T1, this is T2, and this will be your T rated. T1, this is a T2, and this is T rated by W slip, T1 by W slip, T2 by W slip. Now, how we can make that phi or flux constant? Approximately, there is constant air gap flux when Eg or induced EMF is having a very large value, because we know E equal to K into F. That means the frequency into phi. So phi is constant. That means E by F, rather to say A means induced EMF, as induced EMF is proportional with the supply voltage in case of starting or steady state condition. So we can replace this E by V. So it will be more or less proportional to voltage by frequency. So the speed can be adjusted by varying this frequency, maintaining V by F ratio to a constant air gap flux. Now, it's very interesting. See in this graph that there is a torque versus speed characteristics. So, as we know that a starting torque is low, but what will be happening here, as we are varying the flux, this starting torque value is increasing, but the maximum torque value, that means this peak, the maximum torque value remains constant. This is the value for the 10 Hz, this is the value for the 30 Hz, and this is the value for the 50 Hz. For all the corresponding value, the maximum value remains constant. Only what is changing here, it is 600. Correspondingly, this is for 800, and similarly, this is near to in between 600 to 700 value. That means constant flux, rather to say constant voltage by frequency, that is equal to V rated by V flux, that will be having a constant slope, constant increasing value, and depending on this procedure, we are making this voltage frequency open loop. Here is a three-phase supply that is connected across the rectifier. In between, it is connected across a capacitor, VSI voltage source inverter that is connected across the induction motor. Now here we are having the pulse width modulator or PWM, and the limiter is needed to ensure the slip change within the allowing value. Here we are using a ramp function, and by that the circuit is done. So I think it will help you a lot. If you are having any queries, you can ask me in the forum. Thank you all for your patience hearing.